And I'll go right into sharing screen here and clean this mess up. All right, so we're pretty much done with our chasing AI. The 3 states: idling where the character turns, chasing where the character pursues, and jumping where the character stands at just the right distance and jumps up and down. And if we've added this 4th state, flee, which if it's too close, it flees. And I'll remind you, this is a mistake right here. It should be can't jump. So we set this up with an update function. We have our 4 functions: too far, can jump, can see, and too close. We set the animator. We have our logic that assigns the different states, and then we have each of our different states: flee, idle, and so forth. We looked at the controller for this. And I'll remind you that this is an opportunity to use the any state. Any of these 3 states, idle, chase, and jump, all transition to flee. And we could eliminate those 3 transitions and just go directly from the any state if we wanted to. We added the feature of the ability to hide behind something by using a ray cast. And if the ray cast from the eye position, which is an object we put in the head of our AI, if the ray cast from that head out to the target position hits the target, then this is true. And we inserted this into various of our can see, can't jump, and too close functions. I'll remind you of the way the raycast works. It has an origin vector, a position. It has a direction, also a vector, and it returns this hit info that has information about what was hit, the point in space, the distance to it, colliders, rigid bodies, and transforms that it hits. It returns all that information. I also put a gizmo in that we can see in the scene view and in the game view if the gizmo is on, and this draws various lines from the source position in the vector direction, which I use the line of sight vector normalized times the C range to show where that line goes to. And what we did with this was we changed our jump state to an attack state. And we didn't change the animation, but what we did was we added a behavior. We add the behavior to the jump state in the animator controller. What I did here was I put a gun tip on the hand that I wanted the particles to emanate from. This animation state, or this state machine behavior, has these various functions already built into the template: on state enter and on state exit, on state update, on state move, and on state IK. So what we did was in the on state enter, which starts as soon as the animation does, we found from this information that comes in as an argument, we found who was animating it. We accessed their AI script, found their target, searched through all of the transforms in its children for the child named gun tip, and we instantiated our particle system at that point, and then made it the child of the gun tip, so that as the gun tip moved, our particle system would move along with it. In the update function, we kept this object pointed at the player by using the quaternion look rotation that forms a rotation that puts the forward vector of our object in the vector direction between the host target's position and the child position, the child being the gun tip position. And we just kept our AI pointed at the player. And in the on-state exit, we destroyed the particle effect. So all of that is pretty cool. It's a script that you can put on an animator state and have it operate through at the beginning, at the end, and through the duration of that state's existence. The particle effect was just a cone of particles. It emitted 5 per unit distance. So as my AI waved its hands, particles came out of it. I used the collision module set to world, and I had the send collision messages checked, which meant that I could have a health on my player with an exposed variable health, and on my particle system, I could have a health counter that used the on-particle collision. Anytime one of its particles hits something, it returns the game object that it hit. We tested to see if that was the player, in which case we decremented the health by reaching out, getting the component current health, this little script that's on our player, and decremented that exposed variable. So scripts are communicating here. I also added a new parameter, the set mirror parameter, that turns our idle turn right into an idle turn left by mirroring the animation. And this we set in the start function of each of our AIs. We let them decide whether they were going to turn to the left or turn to the right. We made the target fuzzy so that they didn't all follow exactly to the position of the player. We did this with a little random time. So we caught the time plus random time. And then as we set the target, as we obtained the wanted direction, instead of going scrupulously to it, like the line at the top here, instead, depending on how much time had gone by, we threw a random inside a unit circle and kind of made that position that we're going to fuzzier. And we have this random distance that is a parameter, or is an exposed variable that we can adjust to make it fuzzier or less fuzzy. We also did this trick with the AIs so that they can see through each other. And we did this by using a culling layer on the raycast. And the trick here was we put the layer that we wanted it to cull. The culling layer mask is a bunch of 32 bits. And the one that we're culling is a 1, and the one that we've selected is a 1, and the one that we're culling is a 0. And so I use this trick, this tilde AI layer that reverses the bits. So now we're seeing all but that one that we have set. I made a gun so that my player could shoot them. It has 2 coroutines, recharge and fire gun. The recharge just waits every second, tests to see if I've used any of my bullets. If I'm below that number, I'll add 1 per second. And the fire gun fires if this variable fire is true and we have any bullets, and this just instantiates a bullet, gets its rigid body, sends its velocity out in the forward direction with the bullet speed, and destroys it after 3 seconds, and decrements the bullet count, and of course updates the UI. Our bullets can be fired every 1/10 of a second, and if we're not firing bullets, this just goes around every time. Now, here's an important subtle point. The fire is done with input, and input must be done in the update function. We can't do input in an I enumerator because this is not happening every time. Well, it is sometimes it's happening every frame. But if we put our input in one of these I enumerators or in the fixed update function, we will occasionally miss that input. So input should always be in the update function. And so I have this little Boolean fire, and if I press the fire 1 button, it sets fire to true. And that would mean that when the I enumerator came around in the fire gun here and found fire to be true, it would fire our bullet. So we have to do that little trick with input must be in the update function. And this is a common mistake I see even in Unity scripts, scripts from Unity. The bullet prefab is a trigger collider and a kill on hit script with an array of explosions that it can choose among as it destroys whatever it hits, instantiating this explosion. I'll show you that just for a minute here. Let's see, where's the bullet? The bullet has this this kill on hit script, and I put in 50 different explosions. 49 of them are all the same, but one is this special igniter one. And so this means that when I fire my bullet, one time out of 50, it's going to be the big explosion. The rest of the time, it's a simple one. So that's kind of a trick for how to make one thing less likely than all of the others. And finally, of course, to help us aim, I put a reticule in. The reticule is quite simple. We put a raw image in the canvas, and we put one of the sprite textures at the center of the canvas. So that would be position X and Y, both 0, and the anchors centered. So that little reticule, where is it? The reticule is... I don't know where it is. Oh, it's not in this scene. So the reticule is in this scene. So here's the canvas aiming. It has this raw image. We have this little texture. It's set to be fairly small, width 10 and 10 by 10. And it's at position 0, 0 with the center picked for the anchors. And so this will keep this right in the center of the scene. So, and the spawner that I'm using here just starts a coroutine spawner, and it creates AI clones at the position, and it gets their AI script and sets their target. And this is done every so often, every interval. So they come out of the spawner every second, I think. And this will keep the number constant by testing to see if the number has ever dropped below how many I want. So this keeps a constant 30 out there. So the last thing I want to do here is talk about efficiencies, because I've been a little sloppy with the code up to this point. For instance, all of our tests, too close, too far, can see, all of these formed a distance, a magnitude of the vector between transform position and target position. And remember, finding the distance between 2 points is finding the length of the vector, which involves 3 multiplies, x squared, y squared, z squared, 2 adds, add those 3 together, and then taking the square root. And this is expensive. So if we can do this once per time into a global distance, uh, uh, and then leave it out of the tests so that the tests are not each computing the distance, because we have 4 tests here: too close, too far, can see, and can jump. Another tremendous efficiency is to replace the update function, which is performed every frame, with a coroutine that yields these various coroutines: idle, jump, chase, and flee. So this is now an IEnumerator. This is a coroutine, the updater function. And we, of course, in the start function have to start coroutine this updater, but it's going to yield start coroutine idle, and it blocks because this is a coroutine. So it waits until idle is done. If idle is done, it goes on to jump. If jump is done, it goes on to chase, and so forth. And it goes around this little while true loop. In our idle jump, our idle, in our various states, they are coroutines as well. And so we now have the opportunity to put a wait statement in our idle function. This will now wait that interval specified in the wait. And so we can, instead of doing this every frame, we can do it every 1/10 of a second, or every 1/2 second, or however long an interval we want. And this, of course, will affect the behavior of our AIs, how scrupulously they do things, because they'll get stuck in these states as they wait for their 4 seconds. The other thing I've done here is I've encapsulated all of the thinking in this thing called assess state. And so each of the IEnumerators, idle, jump, idle, where'd it go? Idle, jump, chase, and flee, each of these will have this assess state. So things are from a coding point of view, cleaner, in that we've encapsulated all the thinking into one function. And the assess state is, of course, going to calculate that global distance that the too far, can see, can jump, and too close all use, as well as the vector direction to the target that it uses to calculate that distance. And it does all of the setting of the Booleans, and here it does all of the thinking as to which state is going on. So we've encapsulated all the thinking in this assess state routine. And so this makes life much more, this makes this coding much more efficient, because the script is only running as often as we want it to, as opposed to every frame. There's one other efficiency, and this has to do with the culling mode on the animator. The culling mode on the animator has 3 options. Always animate, and this means that our AIs will always be jumping around and walking and doing all the animations. They'll still be moving. Their root motion still is in action, but they don't actually jump or walk. The animations don't play. There's call update transforms that affects the targeting and the IK and some of the transforms. And then there's the cull completely. And with cull completely, the animation is completely disabled when the renderers are not visible. And visible is in any camera. So if you happen to have a map camera that's looking down at your scene, it's going to see all the AIs. And so their animations won't be culled. One problem with this with our dude is that because the particles are emitted over distance, if the dude isn't waving his arm, then the particles aren't emitted. So this may not be a good thing for our system here, but it is something that we can definitely see the effect of here. And I'm going to put this in one of the saved editor profiles that I have, where I've opened the profiler, and the profiler shows us the cost of everything that's going on in our game. And it has stuff down here that shows the percentages that are running here. And we can turn on various different components here: rendering, scripts, physics, animation. And I'm going to turn on the scripting and the animation. And so when I run this stress test, which starts off with 30 characters in the scene, 30 AIs in the scene doing their thing, we can see here in the left-hand window, the dark blue is the cost of the scripts that are running, all of the different scripts, including my players' scripts. And the light blue is the cost of the animations that are running. And you can see the frame rate here is running around 50 something. But if I turn away from them, you saw that light blue stuff go right down to zero. The animations aren't running. And of course, you can also see the particles stopped coming out of them because they're no longer waving their arms. And if I turn back and look at them again, those animations go up. This profiler is really useful for finding what it is that's slowing down your code. If your game is not responding quickly, open the profiler window, start looking through this. It has various things. We can look down through the player loop and see which different components or which different actions in our game are costing the most. We're seeing that the camera render is kind of the top here. The editor loop's using a lot of cycles. The player is this 35% here. So that profiler view is an important tool, and I definitely encourage you to explore this, particularly if your game is performing poorly and you're having a lot of lag. So I'm going to stop sharing at this point and entertain any questions about our chasing AI with the jump attack mechanism that uses these state machine behaviors to fire particles at our player that then damage the player. Any questions? No? Okay. So back to sharing here, and let me close this up. Let me quit this one. And while that's going on, I want to start this generic mechanism and switch into generic mechanism. Now, the animations we've been doing have been with the humanoid form. The humanoid is the animator controller with the humanoid has a lot of things it can tell about the avatar that is attached, and it only works for humanoid characters who have two legs that they walk on, a torso, arms, a head, and so forth. So and we had to configure that FBX in the import. We had to configure it and form the avatar that we drop into the animator controller or into the animator component on our player. But there are other kinds of characters that aren't humanoid in form, and they come with animations too. And working with a non-humanoid, we would, instead of specifying the animation type as humanoid, we would specify the animation type as generic. And often these generic animations don't have root motion. And the example I'm going to show you don't. And if an animation doesn't have a root motion, if it doesn't move with, where's my animations, character assets. So this little mind bot that I've got here has various animations that come with it. And the mind bot is actually kind of twisted. You notice it's kind of sideways in its little thing here. But if I look at the animation for it moving left, it doesn't move. It doesn't have root motion. And so we have to move it ourselves using either rigid body. We can move it around with its rigid body, or we can move it around with its character controller. And I'll show you examples of both of these. With that import setting for the character, we also have the root node that we sometimes have to specify because generic animations don't know how to figure out what the root is. Humanoids do. So the two approaches, we can manipulate its rigid body, and we can do this through the rigid body's velocity. We can assign its velocity, or we can apply forces. We can push it around with forces. The other approach is to use the character controller that we played with back a while ago and use either the move or the simple move function to move our character controller around the landscape. So looking at a rigid body one, first of all, I think I've shown these things require component type of animator and require component type of rigid body. If I attach this script to an object, it will automatically add both an animator and a rigid body component to it, and it will not let me remove them. So this is a good thing. It means I don't have to do various tests. Do I have a rigid body? Do I have an animator? Because this guarantees that one will be there. So in start, I'm going to cache that rigid body and cache the animator. And then in the update function, and here I have actually tested if there's an animator. I wouldn't need that test since this require component forces it to have one. So here I'm going to get the jump button, which is the space bar. I'm going to get the horizontal and vertical axes. I'm going to set my float speed to be h squared plus v squared. And I'm going to set my direction to be the inverse tangent of h over v turned into degrees with the math f radians to degrees. So this is going to give me an angle that goes from minus 180 to plus 180. That is the direction I'm facing in space. So I'm going to set my speed. I'm going to catch a copy of my rigid body's velocity into speed, and I'm going to modify the x and z components with that exposed variable speed scale times the horizontal and vertical components. And then I'm going to assign this back to the rigid body's velocity. We can't access the individual components of rb.velocity. We can't access rb.velocity.x. We have to do this by making a temporary speed, modifying its x and z components, and then storing it back into the velocity. Because this is a rigid body, I don't have to do anything with gravity. Gravity is going to take care of the rigid body. But if I want to jump in the fixed update, which is where one does physics, I'm going to add a force to my rigid body in the upwards direction multiplied by the jump scale, which is how powerful my jump is. Now, the controller for this is fairly simple. It's a lot like what we had with some of our other objects. We have an idle function that is going to operate when the speed is less than 0.1, and a move function, or a move state, that's going to be a blend tree that will move different directions based on the angle in degrees that goes from -180 to 180. So the blend tree here has that direction that goes from -180 to +180. I believe you can see up here -180 to +180, and it has 5 animations. It has 2 backs. It has a back for -180, and it has a back for +180. Because this angle is going to go around behind us. 0 moves forward, left moves at -90, and right moves at +90. So this is our blend tree that's going to blend the forward, left, right, and back animations according to the direction that our character is moving. One other point, since this is a rigid body and we don't want it tipping over, we need to constrain its X, Y, and Z rotations so that it doesn't accidentally rotate. So here, now, let me make sure I'm in the right scene, rigid body. So here's my little spider character, my little spider robot, mine robot. Here it is in the idle state. If I jump, every time I press the space bar, it's making a force up in the air, and gravity pulls it back down again. If I do the left arrow key, it walks to the left. If I do the right arrow key, it walks to the right. If I press both the up and left arrow key, it's blending those 2 animations, the up and the right animation. It's blending those 2 together to move, to make an animation that kind of makes sense. And of course, I had to tune the speed to have the footprints make sense. So alternatively, we can do this with a character controller. So again, I'm going to require component, type of character controller, and type of animator. Again, I have a speed that I have to tune to make this thing make sense. I cache animator and controller in the awake function. MindBot simple move is very similar to what we did for the rigid body. I have the horizontal and vertical axes. I set the speed to h squared plus v squared. Direction is this inverse tangent. And I form a vector in the that is h in the x, v in the z forward, and 0 in the y. I scale that by the speed scale, and I use a simple move. And I'm not fiddling with the jump here because with simple move, we can't jump. And so this is going to look very much the same, except I can't jump. It's using the same animator controller since it's, I'm moving a little fast here. This also, you notice, has the problem that the speed is faster if we're moving on a diagonal than if we're moving on a horizontal or vertical. And that's because my speed is x squared plus v squared, or is h squared plus v squared. So that makes it bigger when we're moving on a diagonal. This is a common flaw in some cheaper games. If we want to do this with the move, again, this is all very similar, except now we've added a gravity, since with the move, we have to take gravity into account ourselves. I have now a jump button for jump. I set the speed and direction the same way I did before. Now I also have the jump button to do the jump animation, and I form a move direction and this little bit was because, remember when I showed you the picture of the MindBot, it was turned on its side. The MindBot's kind of a pathological character. It's twisted the wrong way. Its axes are backwards. And so there's some fiddling that you have to do with it. But if we're also using the controller as grounded, we only can control our character when we're on the ground. Otherwise, our speed is 0 and we're not controlling it. And here's the gravity just sucked out with the time delta time twice for that little physics parabola reason. And the controller, I'll show you that one in a second. So here's the simple move, not simple move, here's the move. It has a jump that lets us jump, and the behavior of everything else here is pretty much the same. It nicely controls our things. We can't control it when we're in the air. And so unlike that first one, I can't continue to jump and keep going higher and higher. Let me show you one more here, and this is now with a two-dimensional blend tree. So our blend tree for the one-dimensional one was keying off this angle that went from -180 to +180 and blended among back, left, forward, and right. And with a two-dimensional one, this is now controlled by two parameters, H and V. Those are the same H and V's that I was get from horizontal and vertical axes. But now I'm going to blend among the right, left, forward, and back based on its position in this 2D little map of things. And since it's a 2D simple directional, I have forward that goes if X is 0. No, I have back that goes if X is 0 and Y is -1. I have forward if X is 0 and Y is +1. I have left if X is -1 and Y is 0. And I have right if X is +1 and Y is 0. And of course, it will blend among all of these as we move our H and V around in the world. And so we can look at this one, the blend, and maybe I can get the controller up here, and I'll look at the move controller, and I'll look at the move controller. So here's the move controller. And so if I move this around in here, it does different animations based on that weight. And so if I play this, and we can watch over here, that's as big as it gets. But anyway, you can see as I'm using the vertical, and so that little button's going over there and it's going forward. I'm using the back and it's going to -1. And so it's switching between forward and back. And here it's going to the left, and here it's going to the right, and here it's going on a diagonal. So you see both the H and V's moving, and it's a blend of forward and left. So all of that's pretty cool. This blend tree one is actually a bit simpler. I cache the various components. I get the horizontal and vertical axes. I set the speed with h squared plus v squared, and I set h and v and jump and I needed h squared plus v squared for the rigid body speed that I had to set, since this doesn't have it doesn't have root motion. And I think I might have also added a little rocket engine to my player to fire a little rocket when it jumps. So we now have a little rocket engine as well. So I'll stop there and discuss generic animations. There's one other legacy animation, which is what one would use with something like LERPs. LERPs was a legacy animation system. And I'm not going to talk about that in here because it's a lot of scripting details. But if you want to go back and look at the wired up LERPs that's in one of the in-class demos, I believe, when we were looking at lights and cameras way back, that character is wired up with a legacy animation system. So any questions here? Okay, well, let me go back to sharing then, and I'll close this one up. Close this one up, and I'll start general mechanism. So when we made animations back some time ago, when we made animations to make our object bounce or to do whatever we did with our animations, when we were using the animation window, we found that when we did that, it immediately put an animator on our object, and it made the default state of that animator controller the animation that we had just made. And we can do that in conjunction with this mechanism system, and we can make very powerful animations of just about anything that we have in Unity. Because you remember with the animation window shown over here, and if I have some object and I create an animation, it's going to let me select the transform, the renderer, the materials, the scripts, all of the different things on our object are options for us to animate. But what I'm going to do here is a little bit tricky, because I'm going to, instead of making an animation that plays through different keyframes, I'm going to make an animation that is a single state. And I'm going to let mechanisms transition mechanism, its transition from one state to another, blend those two states together. So the examples I'm going to show here are sliding doors. A sliding door that is going to get out of the way when a character approaches the door. It'll automatically slide out of the way. And I'm also going to show you some examples with lights. But the idea here is that I'm going to create a bunch of panels that two of them will be stationary in the wall and the other will serve as our door. And I'm not doing this with hinges or anything. I'm doing this with animations. So I've got these set up here. I've got my little door here, and I've got my two walls. And This is a very important point here. I'm going to make the door be the child of an empty game object, the door container. And the reason for this is when I animate the door that's inside the door container, that's a child of the door container, its animations will be relative to its parent, the door container. And this means I can put the door container anywhere in the world, and when I animate it, it will move relative to the door container. If I just animate the door, it's relative to the world, and if I put that door any place in the scene and I play the animation, it will pop back to where I made it. So this is very important. Make it inside an empty game object so that your animation is relative to its parent that you can then put anywhere in the world. So having done this, I select that door container and I create an animation. I've already made one. I'm calling it door closed. So I've made this animation, created it, and I've selected a property, and that's its Y position is at 1.5. Notice here too, I have deleted the other keyframe that the default animations come up with. I only have one keyframe, and that's at this position. So this is the door closed position, is at X0, Y 1.5, and Z0. That's the position of the closed door. I then make another animation, the door open. And the door open is now at position X minus 1.5. So it's going to slide over, and its Y position is the same, and its Z position is the same. So I'm leaving the door where it is. I'm moving the door to be out of the way. And I think we can actually play this and see it move out of the way. So, and again, this is a single keyframe. So with that, I now have an animator that has these two states, door closed and door open. And I have a transition that's going to transition on this parameter, open or closed. And so depending whether this is open or closed, this will close the door. And let's see, I want this over here. And I think this will work. And so if I play this, I have my little character. Oh, by the way, there's a sphere trigger set at the base of the door that's bigger, that's about the width of the door, that is set to be is trigger. And that's the thing that my little character is going to trigger when it walks through the door. And so presto, we have this door that opens and closes as my player goes through that trigger. And all of the transitions are being handled here with the animator. These two states, door closed and door open, are single keyframe states, and they transition using the mechanism system. So that's pretty cool. And so the door container has a child, a sphere collider. Its mesh renderer is turned off so we can't see it. It's set to be is trigger. There are the two animations. Here's the door opener script. As usual, we cache the animator, and then we just use the on trigger enter. If it's the player, we set the Boolean of their animator to open. When we exit the trigger, if it's the player, we set the Boolean to be false. And so this opens and closes our door. And I'll go on with this next time, and we'll animate some lights and do some other stuff. So any questions about general mechanism where we can do anything. And the animator can access the transform, the renderer, materials, colors. It can access scripts and enable and disable them. It can access scripts and call functions in them. It can do a lot of different stuff, but I'll just show you the transform and colors and materials and lights. Any questions?
Is there any situation when you're animating something when you wouldn't recommend using Mechanim
When I would recommend using Mechanim?
or would not? Or
Well,
out of curiosity.
you're automatically using Mechanim anytime you use an animation, because the creation of an animation or the addition of well, no, you can play animations without the animator. That's true. You can just put an animation component on your object, and it then has an animation clip slot, and you put the clip in it and you say whether it's going to play on awake or not, and whether it's going to loop. I mean, you can do it. I don't know why you do it. I think the Mechanim gives you so much more control because it gives you scriptably accessible parameters that you can set to change the speed, to change whether it's on or not. It's a powerful tool. If you don't need it, you don't have to use it. But I can't think of a situation where I would bother not to include an animator on my component, even if it only had one animation that was the default state. I still have then access in that state to the speed, or the mirror. I can make it run backwards. So I don't know. I don't know why you wouldn't use it. It's a powerful tool.
Seems so.
Any other questions? I'm going to stop recording here.